So in chapter 4, it's all going to be about integration. When you hear this word integrate, it just means backwards derivatives. Antiderivatives, and today we're going to talk about something called indefinite integration. All right? Before we get too much into the lesson, I want you to see, can you find a function whose derivative is 3x squared? Write it down on your paper. Can you write something down that if you were to take derivative of it, you would get 3x squared? It's like a guess and check thing. Okay, anybody want to share what they got? X cubed. Anybody more creative than that?
X cubed plus 3.
Yeah. Anybody else? Really, you could say x cubed plus any number. Later on, we're going to call this plus c, and you can see this right here. It's really the best way to write it, where c is a constant. Because we know that when we take derivative of constant numbers, what's the result? 0. So when we're doing antiderivatives, I don't know if there was a plus number at the end. And c could be 0. So, it could be that there's not a number at the end because c is 0. But we're going to have to write it. This is going to be something that some of you are going to have a really hard time to remember. All right. So we use capital F, and I'm going to write this up here like this. So you know how we start with a function. And what we had been doing was we took a derivative. We called that f prime. And then we even took second derivatives. And, we could keep going. What capital F does is go backwards, okay? And this is just a notation to show that what we're doing is we're doing the antiderivative, okay? We call it the indefinite integral. We already integrated on our calculator. When we did the Riemann sum, and I showed you how to do the true value on your calculator, that was a defined or definite integral. We're not going to do that today. We're going to focus on the algebra side of it, like the backwards deriving, okay? Differential equations. We're going to talk much more about this later, but a differential equation is what it looks like. It's an equation that already is a derivative that we're going to go backwards on. We're going to integrate it, okay? We have this theorem. I don't want to spend a lot of time on this. We're not going to do a theorem write-up. It's not a theorem you're going to have to quote and any explanations. But it kind of gives you an emphasis on why we have the C. So if we have something, capital F, it's the antiderivative of F, lowercase f. Capital G is the antiderivative also of F, okay? Then that's only going to happen. If and only if means it goes both ways. If then and then if. If these two things equal each other just with a constant. So let me give you an example. X squared plus 4 and x squared plus 5. What is their derivative? 2x. So if I said I'm thinking of a function and its derivative is 2x, and you said, hey, me too, do you and I have the same function in mind? Not necessarily. But our functions would be the same, except one of ours would be just a number more than the other. This I'm going to talk more about tomorrow, but it's just kind of the same idea of what we already said at the beginning. All right, so let's go ahead and do another example that's going to get us into some of these rules. So if y prime equals 5, do you think you could figure out what just y equals?
Yes.
What do you think?
It's going to be 5x.
Anybody agree? 5x? Sounds good to me. Maybe we should put something at the end of it. Plus c.
Plus c.
Okay, so if I were to take derivative of this, I said, hey, find y prime, it would be 5. So this is good. Now, I do want to write something over here on the side, which is going to seem like a little overkill, but I want to show you, you see all these little dx's down here? And you're going to think, why are there dx's down there? what I'm going to show you is how that works out. And I'm going to rework this problem being a little bit more thorough than just guess and check. What's another way of writing y prime? We're going to say f prime. Okay. Yeah, I kind of asked a very vague question. dy over dx. All right, that's another way to write that. So dy over dx, that is a fraction. It's not like it's just a term. It's a fraction. So the dx thing, I can multiply that to the other side. So I can rewrite this as dy equals 5 dx. All right, and I can integrate both sides because right now, what does the d stand for? What does the d stand for? Derivative. This means antiderivative, so I can do that to both sides. All right? What do you think happens when you have an antiderivative and a derivative? They cancel, and you're left with just a y. All right, now, you see how we have an antiderivative symbol, 5, and then a dx? These two things are bookends, and the thing in the middle is what you're going to integrate. In other words, this is another way to read it. 5 is the derivative of x. This symbol says, what is it the derivative of? Okay? That's another way to say this. Anytime you see this symbol, you're going to see a dx at the end. It could be d some other letter. We know that we can use other letters. But for the time being, and like the majority of the time we do this, it is going to be dx. All right? And so you would still get 5x over here plus c. But at least I hope you can kind of understand why there's that dx there. All right? And this process, I'm going to go into more detail tomorrow because it will help us on problems that are not so obvious. All right, and that's kind of what I just said is basically what it says in the sentence. Okay. Basic integration rules. All right, so first of all, integration, derivative, cancel each other out. You are left with just whatever was there. Plus c. And I have to write the plus c because although I am deriving, what am I doing last at the end? Like, and basically, what do you think the order of operations is? And this is kind of new, so maybe you don't know. So maybe we don't know. That's fine. I'll go over it. So the order of operations here would be you do this, which would be deriving, and then you do that, which is integration. When you're integrating the whole thing, or you're integrating last, either way you want to look at it, you got to have the plus c. So we look at this next thing, and it seems like, well, the same thing is happening. I have a derivative, and I have an antiderivative, and they're going to cancel each other out, and I'm going to be left with, in this case, a lowercase f. I'm not picking lowercase versus capital. I'm using what they have here. I don't need a plus c here. What's the last thing being done to this thing, this function? Or what's being done to the whole function? It's having its derivative taken. So even if you're like, no, there should be a plus c somewhere in here. Well, what would happen when you took the derivative of that plus c? It would go away. So we don't have a plus c there. Okay, right now this may be confusing. When we really do problems, this will not be as confusing because you will actually be deriving and integrating and all that. Okay, so don't stress about that. All right, anybody think they know what the antiderivative of 0 is?
Any number?
Okay, so I'll give you 0, but that's not all. Plus c. Were any of you thinking just c? That would have been fine. Any number, okay? That's because when you derive any number, you get 0. So the antiderivative of 0 is a number. All right, we already found out, so I'm down here right now. We already found out that the antiderivative of 5 was 5x. Can anybody tell me what the antiderivative of 11 is? 11x plus c, of course, right? What's the antiderivative of 29? 29x plus c. So what is the antiderivative for the integral of k? Kx plus c. Perfect. And k here would be a number. All right, the next thing here really is just to show you a main a rule here that's, again, some of these rules I'm just introducing today. I'm not really going to use them that much, but this is a rule that's really going to come into play later on in this unit. But if you have a number times a function, okay, and that's just a lot to integrate, you could say, I don't want to deal with the number. I want the number to move to the outside. So the k can move like right there. So then how, and then once I integrate lowercase f, remember integration of lowercase f, what does that give you? Look at the top of your paper if you need to. Capital F. That's how we denote it. That's just a notation that we use. So we can move that k out to the front, and it makes solving these integrals easier. Okay? All right, the next one is huge. The next rule we're going to use a lot today. And that is, what do you do when you have x to a power? All right, so let's just remember, what would we do if we were deriving x to the n? The n would be moved, it would be multiplied to the coefficient, and the power would be 1 less, n minus 1. So we're going to do the exact opposite. Okay? We're going to, what do you think the power is going to be? Let's do that first.
N plus 1.
N plus 1. Instead of subtracting 1 from the power, I'm going to add 1 to the power. Instead of multiplying that power to the coefficient, I'm going to divide, and I'm going to call this the reciprocal. Because what is n plus 1 times 1 over n plus 1? 1. They're reciprocals. That's what a reciprocal does. And I'm missing something.
Plus c.
Plus c. We're going to practice this in just a moment. So we're going to get a lot of practice on that. All right, next one. Sometimes what you're integrating is going to be super messy. And if things are separated by pluses and minuses, you don't have to integrate the whole thing at one time. You can do it a piece at a time. Okay? So in other words, you can say, okay, I just want to deal with the lowercase f function, and then I just want to deal with this function, g function. Okay, using that notation of capital letters, I want you to rewrite this. Okay, did anybody write something slightly different than what I wrote? What'd you do?
Instead, capital F of x plus c plus or minus capital G.
So you did capital F plus C plus or minus capital G plus C. Is her answer better than mine? Is mine okay? What do you guys think?
It's the same.
Why would it be the
You
same?
have the plus or minus, so either way it's going with the c, they're gonna, right?
Yeah, like C is just some number. So if you're adding a number here, and I kind of wrote it this way just so we could have this conversation. If you're adding a number here, and then you're adding a number here, you can just write 1 plus c at the end. We're going to be a little loosey-goosey with c from time to time. I like that phrase. It fits perfectly for what I mean. All right, so if you don't want to, that's fine, but I will be, and it's totally okay. All right, everybody remember their 6 trig derivatives? It's okay.
It's a great phrase. I really like it.
I use it when it really applies to a situation.
It always applies to every situation.
All right. Well, okay. Let's go over the 6 trig derivatives, and then we will do this. We'll get back on track here. I'll try to get y'all back on track. All right. So forget about what's on the board. What is the derivative of sine x?
Cosine.
Cosine x. What's the derivative of cosine x?
Negative sine.
Negative sine x. What's the derivative of tangent x? Secant squared x. What's the derivative of secant x? Tangent squared plus. This is always where the breakdown
Negative
happens.
secant plus
No.
tangent.
Remember, the derivative of a co is negative. That's it. So, like derivative of co-tangent, cosine, cosecant, those are all negative. So derivative of secant is not negative. It's just secant x, tan x. Okay? What's the derivative of cotangent?
Negative.
Negative. Cosecant squared x. Okay? Derivative of cosecant.
Negative cosecant x cotangent.
Perfect. All right, now, some of you need to study these. What could you do to study them?
Flashcards.
Those green cards that I gave you guys. Okay, the good news is we do not have to memorize 6 new things. You just have to know these 6 things, guys. Because in a minute, I'm going to say, whose derivative is this? And if you don't know, then it's going to be hard for you in this section. So you need to know your 6 derivatives really, really, really well. Okay, so you need to study that if you've forgotten them over the break. All right, so whose derivative is cosine x? Sine x. And we need a plus c here. The integral of cosine x dx is sine x plus c, because the derivative of sine x plus c is cosine x. All right, now watch what I'm going to write next here. Whoa, I can write legibly. I don't know. That was. There we go. What's wrong with this? What's the derivative of cosine?
Negative.
Negative sign. But there's not a negative sign here. There's a positive sign. So what do I need to do? I need to put a negative there so that the 2 negatives cancel each other out. So notice that I'm not giving you a new rule to memorize. Just know the old rules. That's it. All right. Whose derivative is secant squared x? Tangent x plus c. Don't forget plus c. All right. Whose derivative is secant x tan x? Just secant x. That's okay. She's the only one, well, not the only one, but one of the few that's even tried. So don't give her a hard time. All right. What do you think should go here? First figure out what should go here, then figure out should a negative be there or not.
Cosecant.
Don't take the derivative, think whose derivative is cosecant squared. The derivative of cotangent is negative cosecant squared.
So it's negative cotangent.
Right. So I need to write negative cotangent x plus c, of course. And then the last one, same reason, is negative cosecant x plus c. I'm going to move on from here. You just got to know your 6 trig derivatives. Okay, let's practice. Like I said, if you're a practical person, this is going to make a lot more sense as we go through some of these examples. All right. So, number 1, or A, I guess. Alright, we're going to use some of the rules, and we're not going to like quote the rules as we go, but just know we're going to use a lot of these rules that we did on the first page. So when you're integrating 3x to the 4th, there are a few ways I can teach this to you, but I know what works and I know it doesn't. Some of you are going to pick up really quick if there's shortcuts. Kind of like when you learn factoring, and some of you are like, you don't need to do all that work, teacher, you can just do this. If you figure that out, great, good for you. But it doesn't really do the rest of you any good if I just teach you a shortcut. So I'm going to teach you something. If you're thinking in your mind, couldn't you just do this? You're great. It's not like a major shortcut. So I'll move on because I don't want to confuse you. All right. So looking just at this first term, okay, this is how we're going to do it. We're going to write the 3 times. We're going to use that property where you can move that number. Just leave the number there. All right. Now, what's going to be the new power on x to the 4th? What are we going to do that power? 5. We're going to add 1. So leave a space, write your x, and add 1. Okay? What's the reciprocal of 5? 1/5. You're done. Done with that piece anyway. All right, so on to the next one. -5 times, leave a space, write your x, and think, what's the new power? 3. It was 2. We add 1 because we're doing antiderivatives. And then the reciprocal of 3 is 1/3. So that's what goes right there in front, in that space. Okay. Last thing, plus. Leave a space, write your x. What's the new power? 2. So what should go here? 1/2. And then plus c. Now, on a multiple choice, this is probably going to be written as 3/5, and this is 5/3, and that's easy to figure out. You don't have to do that, though. You can, but you don't have to. All right, easy enough? How could you check it?
By taking the derivative.
By taking the derivative. Take the derivative of that. Do you get what you started with? It's pretty easy to check. You can do that. Okay? All right. B. We need to rewrite B. 1/x to the 4th is not working for me. It doesn't look like what we're used to. So let's rewrite the integration symbol. And let's rewrite 1/x to the 4th as x to the -4. And then also write your dx. So I haven't integrated yet. I've just rewritten it. We did this similarly when we took derivatives. We had to rewrite it sometimes before we actually took the derivative. All right, don't let the negative scare you. Just leave a space, write the x, think, what's the new power? What's -4 plus 1? -3. What is the reciprocal of -3? -1/3. Now, if you're thinking, hey, the negative should be with the 1, or the negative should be with the 3, or the negative is out front, all of those things are correct. It doesn't really matter where the negative goes. Plus c. And you could check this by, taking the derivative. You can always check it that way. All right, next problem. We need to rewrite this. How are we going to rewrite square root of x?
X to the 1/2 power.
X to the 1/2 power. We've done that before. All right, so then x to the 1/2. Leave a space, write your x. What would be the new power? You add 1 to 1/2. 3/2. Reciprocal? 2/3. Perfect. All right, plus 2 times. What's the antiderivative of sine x?
Negative.
Cosine. So I'm going to put a parenthesis and I'm going to write negative cosine x, which is totally acceptable. Make sure you put your plus c. How else could you have written that second statement?
Negative minus.
Minus 2 cosine x. That would have been totally fine and probably how it would have been written on multiple choice. But you don't have to do that. You do need these parentheses though, because otherwise you can't really tell if you're doing 2 times or 2 minus. So put the parentheses in if you're going to do it that way. All right, next problem. Good news, there's no quotient rule. Bad news is we have a quotient, so we have to deal with it. Okay, but we don't have a quotient rule and a product rule for this. Okay, you just have to rewrite it and deal with it. There is a form of a chain rule, but it'll be a while before we get to that. All right, so I'm going to kind of help you out with this. We're going, since this is like x plus 1 over the cubed root of x, I can rewrite this so that it's x over x to the 1/3, because 1/3 would be the same as writing the cube root of x, and then I could say plus 1 over x to the 1/3. You can do this when your denominator is like a single thing, a monomial. We could not have done this if this was like cube root of x plus 2. That wouldn't have worked. We couldn't even do the problem. Okay. Don't forget dx. All right, we need to do one more step of simplifying before we're ready to integrate. So right now, I have x to the 1 power over x to the 1/3 power. What are we going to do here to get just a single x? What's that algebra skill? So if you had like x to the 5th over x squared, what would that simplify to? X cubed. You would just simplify the powers, or you would subtract the powers. So you're just going to do 1 minus 1/3. And again, you're not doing any calculus. You're just simplifying. So don't forget that you still need to write the integration symbol.
Oh, okay.
Okay, we haven't done any, that part's next. We're still just in the algebra prep stage. All right, what about the next thing? How could you rewrite this so that's not a fraction?
X to the negative 1/3.
Exactly, x to the negative 1/3.
You will need
All right. Okay, so let's finish this one out. Now we're ready. Leave a space. What's the new power? X to the 5/3. Some of you are better at this than others. If you're like, ooh, how'd you get that so fast? You need to practice your fractions. Do not use a calculator when you're doing this. You need to either do this in your head or do this like using scratch work paper or something. But you got to be able to do that without a calculator. What's the coefficient? 3/5. And if there had been a number here, I would have just written the number times 3/5. All right. Next would be plus, leave a space. What's the new power on the negative 1/3? Negative 1/3 plus 1 is 2/3. So then the reciprocal of 2/3 would go in front. And plus c. Now, when you check something like this, if you check the derivative, it won't give you what you started with. It'll give you here. So you have to make sure you're doing these beginning algebra steps right. There's really no way to check that. Okay, last problem. We went over the trig stuff on the first page, and that didn't go over so well. So this might be difficult. But was there any of the trig that when you took derivative of it, it gave you sine x over cosine squared x? Were any of the 6 trig derivatives equal to that? No. So I need to change the way that looks. Remember that trig proof chapter? Remember trig proofs, guys? Maybe you blocked it out. Okay, so this right here is a skill you would have learned in that chapter, hopefully. Can you see any identities, easy things to take out and replace?
Sine over cosine is tangent, and 1 over cosine is going to be what is it?
That's right. Sine over cosine, that's tangent.
1 over cosine is
This is like 1 over cosine is secant. And notice I'm still writing integration symbol in dx because I haven't taken the antiderivative yet. I haven't integrated yet. All I've done is rewritten the original statement into something new that I do know is the derivative of what? What is, and you're really used to seeing this in reverse order. So secant x.
Let's see.
Let's see. Don't do all that work and forget your plus c. Don't be that person. That hurts when you get that graded quiz back. Okay, so you don't need to know everything you learn in trig proof world, but this is what you do need to know. You need to know that sine x over cosine x, and I'm going to suggest that you write this down because you got to write stuff down, you got to see it, you got to say it. This is how you remember things. You got to know this. What was the other one that was like this? Do you remember? Cosine x over sine x is equal to cotangent x. You got to know that 1 over sine x is cosine x. You got to know that 1 over, oh, that's not right. I'm just an autopilot towards the end of the day. Sorry. What's 1 over sine x? Cosecant. This is the reciprocal identity. What's 1 over cosine x?
Secant x.
Secant x. 1 over tan x is cotangent x. I'm not going to write that down because you don't use it as much. And then the last thing you may use from time to time is the Pythagorean identity. And there were actually 3 Pythagorean identities, but if you know this one, you can derive the other ones, okay? So these are identities for the most part students remember. I mean, there were some weird ones, like sine of 1/2 a and all that. We're not really, if you decide to become a math major, you may just use more of those, or if you just take several semesters of calculus, you may need to know more trig identities. If you become an engineer or something like that. But for this class, this pretty much covers you. You never know what could be thrown out on the AP test, but we're not going to focus on what we don't know. We're going to really focus on what we know. And if you want to dig out your old trig sheet, you could. If you have